Good morning, everybody. It's my great privilege and honour to open this discussion on smart grids. I was going to end with a comment about cybersecurity, but John did a very nice introduction there, and I'm inclined to sort of build on it. As we've thought about the application of smart grids, I mean, particularly on electricity transmission, where the criticality of the grid is so high, where a lot of transmission engineers would argue that we already have smart grid actually, and have had smart grid for a very long time, because that's what's needed to run economically an electricity transmission system. But when we talk about making transmission systems even smarter, people are coming up with some fantastic concepts about detecting changing conditions, potentially faults, in milliseconds or less, redispatching the source of power in milliseconds over very large amounts of power over very long distances, and being able to do all that in a way which keeps the system secure and avoids potential cascade tripping. And you can come up with the great opportunities of technology, you can come up with amazing schemes which would deliver absolutely huge amounts of value to customers by optimizing the system in a much more active way. But at the same time, we see all of the risks about cyber developing, and I just wanted to introduce that by saying I was sat in a meeting with some of my people about 6 months ago, and they said, if we get this wind off North Wales, and we get the nuclear power station in Anglesey, and we get this and we get that, then the smart grid way of dealing with all this without having to apply for new routes would be to do this. And they came up with a very, very clever system. And I said, well, I'm not sure I'm really in favour of taking this forward. I don't want to seem like a Luddite. The problem I have with it is this particular scheme, it was resting such criticality on these systems that I ended up saying to them, I might be brave enough to build something like this, or to have the organisation build it, but I doubt my successor, assuming it would take a few years, would be brave enough to turn it on. And so that's one of the big tests that we need to think about as we develop all of this. Will operational managers be brave enough to turn some of this stuff on? So we've started at the very elegant and exciting end of this, and John mentioned low carbon economy and the transition to a low carbon economy. But I thought I'd start by talking about, if you like, the world prior to the transformation of energy. And that's a world where we have a level of smartness deployed. On the transmission system, if somebody flies a kite up into a 400,000 volt line, or it flashes over to a tree, or we get some wind-blown debris, then over tens of kilometers, potentially even hundreds of kilometers, massive circuit breakers that are sort of the size of this room will open within 100 milliseconds. That's really astonishing. We've had that since about 1960 or thereabouts. And so there and always has been, a degree of smartness applied to all of these things, and it's been applied extremely successfully. But the story of the extent to which that smartness has been applied is a story about economics. To take the other end of the network, on the low voltage end, when you're on very distributed feeders, actually the level of smartness is very low, and that's not because it hasn't been possible, it's because it just simply wasn't economic. So the advances in processing power and the price of processing power, the advances in digital communications, the advances in measurement technologies would mean that even if our energy systems weren't changing, even if the sources of electricity and gas and the uses of electricity and gas were staying constant, we would still be talking about this today, because the economics of deploying smart technology has changed dramatically, and that alone would lead to this being an era of deployment of smart technology. That much cheaper ability to deploy technology with much greater functionality will give the opportunity for us to know a lot more about the operational state of all of these networks, and to know it very, very quickly. And that's of huge value to our customers, because it means that we can provide the customers at the same price with much better service, much more reliable service. I'm talking about security of supply, avoiding power cuts and loss of service to customers. So there's something there about applying smart technology deeper for reliability. There's also great opportunities in the smart technology that's available now to allow much greater, deeper condition monitoring of assets. And as we look at what can be done, we realize that what's been done for the last 40 years, even on transmission systems, is relatively rudimentary. The measurement systems we fit to HV transformers to ascertain their health has really been relatively limited. We do things like oil sampling, as many of you will know, for dissolved gas. There's some monitoring of RF. There's obviously very fast acting protection locally to try to protect this equipment. But the opportunity to deploy much, much more sophisticated condition monitoring offers two key benefits to our customers. Firstly, it offers the benefit that we can prioritize our maintenance in a much more intelligent way, so that we're not just visiting assets on a routine 2-yearly maintenance schedule. We visit them and look after them when we need to look after them. And that, of course, makes us able to deliver our service much cheaper to customers. The other key benefit that better condition monitoring can deliver is to allow our asset replacement decisions to be made much more intelligently. If we really understand at all times the exact state, the exact health of each of our assets, looking right across the system, transmission and distribution, the same as applies to electricity and to gas, then we can sweat the assets more, we can delay replacement of assets, we can make sure that we are exactly prioritizing in terms of criticality and health the replacement of the assets across the system. And bear in mind that our networks are aging. Well, I suppose we're all aging. But our networks, you know, when I was young, the networks were young. Now I'm middle-aged, and it happens that networks seem to have less age in them than I'm hoping for, and so they're old. So, so as we get into the replacement phase, with billions and billions of pounds to be spent on replacing our aging assets, the benefits to customers out of us being able to replace just in time and to prioritize our asset replacement will be very, very significant to customers. And some of you will have seen probably footage last week just to demonstrate the point of up in the northeast of a rather large fire at a place called Creaky Beck, where one of our 400 to 132 kV transformers faulted and caught fire. And these are very serious incidents with not just implications for customer service and economics, because we now have to replace that, but also environmental issues about huge plumes of smoke and so on. So much better and faster condition monitoring will be of great value with that. But you know, that's sort of what we would have known 20 years ago. The move to low carbon energy systems creates all sorts of other opportunities for value from smart technology. On high voltage systems, deployment of renewables in particular dramatically changes the operational characteristics of the high voltage systems. A lot of the renewables, and this is true of nuclear as well, of course, where they're built at scale, will be much further from the demand centres. That means we've got to ship more power over more kilometres in an environment where getting public consent for new corridors and new assets is rightly a very contentious issue as we go out to consult with stakeholders. So being able to drive more power intelligently through the existing corridors, the existing assets, is going to be very valuable. Renewables, as we all know, are intermittent, and as a sort of slightly separate characteristic to intermittency, let's reflect that they're often not there when peak demand is there. Now, you might see that as part of intermittency. I wouldn't particularly fight you on that, but that's a critical issue, actually, as we think about the fact that networks and the systems are essentially built to deal with peak conditions. They have other more techie characteristics which make smart grids valuable in the deployment of, in a world of the deployment of renewables. They lead to a system with much lower inertia on it. That means the system is much more flighty, frisky, it moves around more, the technical characteristics of it, the stability of the system is inherently lower. And that means that fast-acting controls become much more valuable in a world of major deployment of renewables. Of course, we're still holding our breath to see whether we will get a new generation of nuclear built, and discussions are continuing between government and developers on that. It's all part of the energy bill that's before Parliament at the moment, as many of you, and I'm sure all of you know. The new nuclear units which are being proposed, though, are a bigger size, and we have to reflect that we are an island system where we already have a frequency trace, the measure of the balance second by second of generation demand, which is much more variable than where you have larger AC systems such as the United States and let's call it mainland Europe. So deploying these larger nuclear units in particular means that every second we will need to balance the system for the possibility that instead of losing Sizewell, which is 1320, we will lose potentially Hinkley at 1800. And even if the nuclears aren't deployed, the same issues are coming about how we connect offshore wind. So wind out in the Dogger Bank may well be connected through circuits that carry 1800 megawatts. And so smart grid applications to help us manage that increased cost of balancing the system against the largest instantaneous loss will be very important. We will also need to find ways to use energy storage and demand, I'm going to call it demand shifting. Energy efficiency is another issue we could discuss, but let's just call it demand shifting at the moment, to help us balance the system more economically. In particular, it still haunts me that, of course, in the middle of winter, on a demand of about 50 gigawatts over the tea time peak, we get a sudden 5 gigawatt increase. That's a very large increase, and that costs money for customers, and any ability to have smart meters and smart signaling to customers to move demand away from some of these peaks will be very valuable. It's worth just talking about gas. On high pressure gas, there are a number of very similar type of technical challenges. In particular, as you'll all know, I'm sure, between 2003 and today, we've moved from being self-sufficient in gas from the North Sea to the North Sea only providing about 40% of our gas. Where's the 60% that's missing come from? Well, it's coming from world markets through interconnectors to Norway, through interconnectors to the rest of Europe, and through liquefied natural gas terminals in South Wales and Kent, fed by ships coming in mainly from Qatar. Now, why do I reference that? Because when I talked about needing to ship more power in a more variable pattern on electricity because of the deployment of renewables and nuclear, the same thing could be said of the gas system these days. We used to know where the gas was going to come from. It was going to come from the North Sea, predominantly in St Fergus and Bacton, and it was going to flow down through in a pretty predictable way to the demand centres. And remember, we are extremely gas-intensive society, with gas being deployed massively for space heating. So what's happened now is, with the displacement of a significant amount of North Sea as those reserves become exhausted by gas coming through a variety of different places geographically in the UK and geographically globally, we find that the movement of gas on the system is much more variable and changes very fast. So again, looking at measurements and processing that can allow us to optimize the gas system is going to be very important to customers. But then moving back to electricity, I talked about the high voltage position, but I wanted to talk about low voltage, and then by which I mean distribution systems, and then try to finally bring it all back together. So the changes are even more profound on the distribution systems. On distribution systems, we're going to see much more distributed generation. We're already seeing that quite significantly. We are therefore going to see those distribution systems go from being essentially passive, where the power just flows through them, to active, with generation coming on and off, much of which could well be intermittent. I mean, just let's reflect on Germany for a second, a system which has 31 gigawatts of solar on it, most of which is distributed. So by looking at some of these other countries, we can see what's ahead of us. The ability to invest enough and to control those systems using smart grids will dramatically improve the economics of that journey that we're going through. And then, of course, you will have been expecting me to talk about not just the transition of the electricity system to a low carbon system, moving from it being the highest carbon intensity of our energy systems at the moment compared to oil and gas, moving it through to be the lowest carbon intensity, sub 100 grams per kilowatt hour, leading to the opportunity to decarbonize transport and space heating, which currently come in at 200 or 300 grams per kilowatt hour. We cannot underestimate, this is probably the most profound challenge we have out of all of these challenges. Currently, on a peak winter day, there's 3 or 4 times as much energy going through the gas distribution system than through the electricity distribution system. Just imagine if you start to move significant amounts of space heating onto heat pumps, which then shift load from gas to electricity. How quickly does the distribution system in electricity become overloaded? How quickly do we start to struggle as an industry to be able to invest quickly enough to potentially increase the capacity of the distribution systems by perhaps 3 times? That's going to be a massive challenge for us if we see fast decarbonisation of transport and space heating. And there's a great joke which plays to all of this, which is a bit of a chance for audience participation. So how do you tell the street that has a major deployment, lots of people with electric cars? John's heard this joke, so is it the people that have solar panels on their roofs because they're obviously very green, or is it the people that have very big houses because they can afford expensive electric cars, or is it urban places where electric cars will have a shorter? No, it's the street that has the distribution transformer at the end of the road on fire. And that speaks to the issue about the loading on these distribution systems. So that's all very exciting, but I just want to finish by talking about how it all comes together, because how it all comes together is a truly fascinating question. So imagine that you get home in your electric car. You're one of those people with the solar panels and the big house and so on. You live in town, and you plug in your car. In this smart grid world, does it charge straight away, or does the controller sit there saying, no, don't charge now? And I quickly sort of tried to jot what I thought was the start of a sort of decision tree for this thing. So the answer is yes, it does charge straight away, unless you've asked the controller to pick the cheapest half hours overnight, or it may not be overnight, because of course it might well depend when the wind's blowing strongly enough. So yes, unless the controller decides this isn't the cheapest time, and unless there are low voltage constraints on the system, which means for your car to come on at 5 kilowatts, this is like turning on 2 kettles in every house, but not just for the 90 seconds we normally have a kettle on for, but for hours. You know, imagine the stress on systems that we're going to have. So it will, unless low voltage constraints on the system are binding. But even if they're not binding, there may be high voltage constraints binding on the system, in which case the smart grid would want to put an interrupt on that charging, and obviously pay customers for the privilege of doing so. And there might be another no box in here if that particular demand has been registered through the smart systems to be on frequency response, and we've just had a large generator trip on the system, which means that we've then called some demand resources to balance out the system economically in the short term. And assuming that none of those no boxes trigger and your car does start charging, then how does the system decide then how to re-optimize your requirements for wanting to know it's going to be charged exactly when you want to use it, later in the day or in the morning? And if some of those no triggers have been initiated, at what point during the evening does the controller then recalculate all of this and say, okay, this is all very well, but I'm getting a solid no for all of these reasons, and yet the owner of the car wants to drive it in 3 hours' time, so now we'll override. And even if you can solve all of that for one car, how do you solve all of this for, what do we think, 20 million cars, fridges, heat pumps out there? And to the extent you integrate all of that into, you know, a very significant centralization of all of these decisions, let's return to the first point. How then do you make sure that that is secure from a cybersecurity point of view, can't be interfered with to lead to, you know, major shutdown of the system? So they're my introductory comments about the exciting world of smart grids. Just fantastic technical challenges for us to wrestle with. Massive value for customers, but some very serious issues to solve along the way if we're to do it in a way that really delivers value and secure, reliable service for our customers. Thank you.